Hello everybody, welcome to my devlog. Today I want to talk about how voltage is handled in my game, voltage in general, how it was handled before, and how I'm working on improving it. I will also touch on the history of the game and hopefully not go as long as last time. So the main inspiration for this game was a game called Matter that I've seen RCE play on his YouTube channel, and it looks a little like this. If you're not familiar with the game, basically you have these nodes here, they produce numbers. Numbers move along these belts, and then you have to deliver a certain number of the numbers into here. And you have to add them, subtract them, etc. Things like that. So I thought, let's make a game where instead these are crystals. And the crystals produce charges, and the charges move along conduits. And you have to deliver a certain number of charges per second, which is current, to the output. And that's how you drive your different devices. And that was kind of where the start was. And so that's why at the beginning, everything was current and there was no voltage. Voltage wasn't even a thing that I had. So I had everything built on current. The numbers that moved through, they were charges in columns. Columns, or however you count that. And yeah, that's why the first level, the one level, has a little power gauge up there. That was the amps that you needed to put out of current. But as the game evolved and grew over time, it moved quite a bit away from that initial design. So, and I ended up, one of the things I wanted to be able to make logic gates, things like that, and that you really start bumping up in the voltage when you're doing that. I did manage to get pretty well with only a kind of sense of voltage, but essentially the initial thing that I've done for getting around that was when these little numbers here were generated, they would carry with them the voltage of the crystal that generated them. So they pass along. When they got to the emitter would know the voltage, and it would pick up resistance all along each one of the conduits. So each one of these conduits, they have an internal resistance, like they all have resistance. The poor conduits have a 0.1 ohm, so they have pretty high resistance, kinda. But the good ones, they have the same resistance as a copper wire, so they're pretty much negligible. But it would add them up as it passed through each element, and then when it got to the end, it would have an idea of what the total resistance along the path was. And you can kind of tell from this, you've got parallel paths. That's not quite accurate, because that's not the actual resistance. Well, this one has a battery, that's not accurate. That's not a good example. But when you have parallel paths, the resistance isn't. You do have to consider the parallel paths and the resistance when you're calculating out the power and the current. So I have to do that. But we're getting ahead of ourselves. Essentially, these would carry them. They would say, the current was the voltage over this cumulative resistance here. That was I. The power that it generated was I squared over the resistance of this room. That's how much power this room had. Each one of these dissipated power based off of I squared over the times the resistance of the individual elements. So they would have to dissipate that power. Each one has a particular dissipation in watts that they can do, and if it takes more than that, if it goes over that amount of dissipation, then it starts to overheat. If it overheats too much, it fries. We covered that in the last video, so I won't go too much into it. But yeah, that was how voltage was handled. It was discrete and it was carried with it, and there was no such thing as voltage drop, which is fine. So about the time I thought, you know what I want? I want to have a puzzle that's an analog to digital converter. And you can't do that like this. You gotta have voltage, and you gotta have voltage going correctly down parallel paths, which this most certainly was not. Let's go ahead and delete these ones here. And I'll kind of demonstrate what I'm talking about here. So let's start down here. And for this, we'll just have 2 emitters like that. If I can click right. So go that way, go that way. Let's just do that and put a switch in there. Just because this code might still be able to go on the other side, and I know that changing this refreshes the. So in this case, yeah, we got. So this would be what I would be talking about if we were talking a parallel path, because these things are considered ground. Every one of the emitters, well, not every room is a ground, but emitters definitely are. They separate based on the types, so they have some consume charges, some do not. But these, let me see here. So, the resistance, sorry, I had to stop and gather my thoughts. So, the resistance that this source is going to see, like if this were a battery, for instance, and it were going to ground or some voltage source, the resistance that it's going to see is going to be the sum of this, all of these resistances, but up to about here, and then things get messy. You see, because these resistors, they're all in parallel, and technically these are all in parallel as well. Well, they look like they're in series, but once you branch, you're parallel. So you have these ones here. You got 1, 2, 3, 4, 5, 6 on this branch. That'll be 0.6 ohms in this case. 1, 2, 3. Sorry, not 6. This one has a resistance of 10. So 1, 2, 3, 4, 5. 10.5 on this branch. 1, 2, 3 plus 10, 10.3 on this branch. And this one has 0.1 as well, so we'll count it. 1, 2, 3, 4, 5, 6. So up to here we have 0.6 ohms up to the branch. Branch itself has 0.1 ohms as well, so we'll call that 7. 0.7 specifically. So then we need to take that 0.7 and then we take so you add those up and then you take the reciprocal of that 1 over and then you add it to these resistances, and that's going to give you the resistance of this. So when things are going down this side and this side, they'll be taking those things into consideration, and that is what the total resistance of the circuit, including all branches, is going to be. And I don't know that number off the top of my head. I've had to always do calculations or go into the thing and look at what it says. But the main thing is you need to be able to calculate all of the resistances that it's going to have, or you're not going to get a very valid result. So the main thing to note when it comes to the voltage is that the voltage that this is it's not going to change unless, say, I press this switch button. At that point, it has to recalculate the resistance on the entire thing because of that, and it also needs to propagate voltage appropriately. Because obviously, if I click this, well, now there's no voltage going downstream because I cut off the only stream. It is a little bit different if I add in another one, but that I don't think that's set up to work right now correctly, so I'm not going to. But earlier, if it was working, actually, you know what? Give me a second. Okay, we're back to blinking lights. So you can see here, kind of remade the circuit from earlier, but yeah, what I was saying is you turn this off, you see these ones go, but now this one can allow this to go. And that's because this particular one does not have a switch on. Okay, I got the blinking lights back. So you can see here when this one's clicked, then it's able to travel that way. There we go. This one clicked, travel that way, that way. That's not really relevant to what we're saying, I don't think, but Yeah, I'm still trying. I'm trying to work out what needs to happen when you have two voltage sources coming together. But let's. Now that we went through all that trouble, let's go ahead and delete it. So anyhow, but yeah, now I have because it goes through the tree and it calculates out its voltage drop and it calculates out that. I can look here, I can see that this thing, here you have 9.8 volts there, and or 8.9 volts, I'm dyslexic, and over here we have 8.1. Because each one of these has a 0.1 ohm resistance, so if you want to go do the math, you can. This is a simpler one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And it's 1.1, 1.2. 2.2 ohms is the total resistance of this circuit. So with each one of these being 0.1 ohms, you can kind of work out what the voltage drop is. This one has a voltage drop because it's 10 ohms to ground, basically. So you have to consider it as being primary, both a resistor and a path to ground when you're calculating. Ignore the power, it's incorrect. I think the current should be correct. Well, anyhow. So the reason why I felt like doing this was, as I mentioned, I wanted to make one of these as a puzzle. This is a flash ADC 3-line, 3-bit analog to digital converter. So it'll take analog along this, which is the V, and this is the thing that you want to know what the voltage is, right? And over here you have your reference voltage. This is a known voltage. Probably something like 9 volts in our case. So it needs to go and it needs to encode these 8 lines into that. And that means 3 is less than 9, so this comes low, not high. And that'll continue until probably around here. I should give different numbers and actually did the math on them, but whatever. The main thing is the voltage drop and the split off from different nodes at different sections. So it's the key thing when it comes to dealing with this sort of ADC. There's also, let's see here. It's also this image, which might be a little intimidating, but it's not too bad, I don't think. The main thing is these things here, they're XOR gates. These are something you'll make in the game, so you'll understand it. All of this stuff here, this is that priority encoder that we saw right here, right? This is our 8-line to 3-line priority encoder for binary output, right? So that is what all of this stuff, basically everything over here is. So that would be its own puzzle as well, be making one of these encoders. Whether it's any different than a muxer, I don't know. I'll have to look into that. So I should also probably point out that I am not an expert when it comes to making, when it comes to electrical engineering. Like, I've had to learn basically everything I know in the process of making this game. So I'm going to get a lot of things wrong. Feel free to point them out in the comments. But yeah, that's the main things here. These are just XOR gates. This is ground diodes along this way. Now for my game, every wire is a diode, so that's probably not an issue. And yeah, they just connect to different areas. And down here to this, these are where the outputs actually branch off. In my game, I do have these bridges that allow you to go over wires. That's important. I've been meaning to add that into the display. Essentially, a bridge. So with bridges, what you can do is you can take something like this and go ahead and put an emitter up here, add in a switch, because why not? Now, what happens is when you hold down the shift key and you do your drag, now instead of this being a merge into there, it's instead going to go over it, and you can tell by how that is there. So we'll start it up. Hopefully I actually connected the switch all the way, and that all the way. Okay. So yeah, now you can see they're going over. I just wanted to do that. Yeah, because one of the things, so one of the reasons that I've done this was for the quick response like that. Because previously, I think you saw in a previous video, when I would click on one of these, all of these would still make their way all the way up there. I don't want them doing that. And essentially, it meant that there was hard times because it depended on those packages arriving at a particular time, and so how long should I? And this would flicker a lot. So it still flickers, but it flickers for the right reasons, because this is varying. So it basically holds on to it till another one arrives, or if the voltage goes to 0, then it's all there. So you can have these two, and now you see they're not getting blinking lights over here. We're getting proper crossings, which is what you need, especially because a lot of the electronics-based puzzles, they require things to cross over each other without interfering. What was that? The XOR gate, I think, was the first one that it came up that really needed that. So you kind of got to cross each other. The AND gates and the OR gates, they're fine. They don't mind. Right now, because I have this code in a broken state, there's a 0% chance that the transistors work correctly right now. So I won't be demonstrating. But yeah, this has been a somewhat brief update on what I've been doing here with voltage and getting voltage drops in, getting I'm going to go ahead and record that part again. Just try to get it with a little more energy, huh? I don't know what you're going to say. Oh yeah, one other change that I forgot to mention was actually related to the routing. I can't see in this one, so let's just go ahead and stop this circuit here. And we'll go ahead and don't do that. This one, no? This one. Branch off here, put one over here, connect them, and we'll go ahead and reconnect. So, one of the things about this is how it actually decides on the routing. Previously, it was just round robin, you know. It would go this one, then this one, then this one, then this one, this one, etc. As long as it could get one out there, that's what it did. But now, instead of that, it uses a Monte Carlo approach, choosing between them with which branch will take is weighted based on the resistance of that branch. So it'll send things down more preferentially down ones with less resistance than ones with more resistance. I'd mention that here. So that's what I've been working on. I'm still learning a lot about electrical engineering. I don't think the ADC will be in the demo, but I think it's still a good idea to get the voltage working correctly. With this, I might even be able to get the capacitors back to working like real capacitors. And then that opens up RC circuits. And think of the fun things you could do when you have an RC circuit to shoot fire. Something like that, you know? Or who knows what sort of item I'll come up with in the future. Or if anybody has suggestions, that's always good. I do know I'd like to have a puzzle for the 555 timer. And you kind of need an RC circuit for that, so that's an option right there. But anyhow, that's what I have. I am currently uncaffeinated and I'm tired. So, see you on the next video. I don't know what the topic will be. This one was on voltage, maybe we'll cover resistance. I don't know.